Konnichiwa ninjas, this is Sensei Silvers and welcome to the Environmental Physiology Lecture Series. In this first episode, what I'll be discussing is some of the basics of thermoregulation and how humans respond to unique environmental stressors. In the subsequent episodes, what I'll cover are some of those unique responses and adaptations to cold environments. I'll have an episode on hot environments. And then finally an episode focused on higher altitude environments. This is a fun lecture series for me. I certainly hope that it resonates favorably for you too. And I think that's all I can really say. So let's get this thing started. Tune in, XViz Ninja. The first thing to discuss are some of the basic human responses to environmental stressors. So, like I have referred to exercise as a physiological stress that your body then responds to in a very specific way, the environment imposes unique stressors that your body then has to respond to in specific ways. I'll discuss what some of those specific responses are in some of the subsequent episodes on cold physiology, heat physiology, and altitude. However, what you need to know is there's just some basic human responses that most people generally exhibit in response to environmental stressors. So in reference to your ninja notes, you'll see a big list there. I won't speak about all of them in this particular episode, but rather I'll speak to some of those important themes or trends more generally. So first, as I mentioned, each environment presents unique stressors. Those stressors will disrupt homeostasis in one or more body systems. Maybe that's the pH of the blood, or that's the temperature of the blood. And in response to those homeostatic disruptions, you'll see very specific acute responses. And again, this happens in all people. Where you will see variance is in how people respond. What's the magnitude of response? Sometimes those responses are positive, sometimes those are negative. Again, I'll cover that in more detail in some of those subsequent episodes. Number 3, for each type of environmental stressor, it doesn't matter if it's cold or heat or altitude, generally speaking, if you are exposed to that environment chronically, meaning multiple hours a day for about 1 to 2 weeks, you will see adaptations to help respond better to those unique environmental stressors. In an environmental physiology context, we call those adaptations acclimatization. I know it's a big word, lots of syllables, but I want you to get that down. Okay? So most humans will acclimatize to a very specific environment if they've got the right kind of exposure in 1 to 2 weeks. The cool thing is once you've acclimatized to a specific environment, you can keep those adaptations for upwards of 2 to 4 weeks following removal of that environment. So if you move to a place of high altitude for a month or 2, after you move away, you're going to keep those adaptations for maybe another month. And as you'll see, spoiler alert, in the altitude physiology episode, that has some real performance benefits tied to it. Now, everyone can typically acclimatize in 1 to 2 weeks and keep those adaptations for 2 to 4 weeks. However, some people have genetics that allow them to respond more favorably to certain types of environments than others. And that's this next point here. Some people are just built for altitude well. I think of the Sherpa populations that live in Nepal. You've got these people who have essentially evolved to handle high altitudes better than people whose family grew up at sea level altitudes. Each of you has a particular environment that you've already acclimatized to in the past, or you just tend to favor more than another, maybe because you respond better to that environment. But blending with the previous point, it doesn't matter if you've got good genetics or not for a particular type of environment, everyone can acclimatize to any environment. Now, if you've got good genetics, you'll probably acclimatize to a specific environment faster than someone who doesn't, and you'll probably respond better. You'll probably see physiological adaptations that allow you to handle that environment even better. But everyone can acclimatize to each type of environment, even if that acclimatization isn't as much as someone else's might be. The next point, it's worth mentioning that the physiological responses that we would observe for an individual responding to unique environmental stressors, those physiological responses can be appropriate or completely inappropriate. So if someone doesn't respond well to heat, raising my hand because that's me, I don't respond well. So the physiological responses tend to be really exaggerated. And in cold, the physiological responses I would see tend to be a lot more muted than they might be for someone else. Again, I'm sure that you all probably have your own stories or experiences you can think to where those responses have been exaggerated or muted in some way. And that leads me to the next point, psychology. How we view a particular type of environmental stressor will indeed influence the physiological responses. So some of you may be familiar with Wim Hof. He's an individual who is known to overcome a variety of extreme environmental stressors, and he believes that everyone can essentially train their mind and their body to better handle some of those unique environmental stressors. The point I'm trying to really make here is that that psychological piece is really important. It's real, for one, right? This isn't just, hocus pocus made up stuff. How you view that environment can have favorable or unfavorable physiological outcomes. So since I know that I don't handle heat very well, I need to think more positively about heat when I am presented with a hot, dry environment or a hot, humid environment. When I'm exercising, I literally need to think happy. Happy thoughts do go a long way. And in fact, that psychological, physiological link is so powerful. This is the last point I want to make on this, is that if you start to think about a specific type of environment, even before you're exposed to those unique environmental stressors, you may see some of these specific physiological responses tied to that environment. So a great case in point is if I'm in an air-conditioned building and I know it's just super hot outside, if I start to think about the fact I'm going to walk outside and it's going to be hot, I might actually start to sweat before I've even gone outside, before my core body temperature has even increased. In effect, that sweat response is trying to pre-cool me before I go out. So that psychological piece is huge. And the main message I want you to get from this is think happy.
Clap along if you feel like happiness is the truth.
Happy thoughts go a long way with regard to how your own body responds to some of those unique environmental stressors. Okay, so enough of that. Let's go ahead and move into some of the basics of thermoregulation. Okay, it's time to discuss some of the basics of thermoregulation. The first thing that I want you to understand is that your brain basically has two components. There's this basic part that controls primary living functions, and then there's a cerebral cortex on top that is responsible for a lot of voluntary responses, cognitive tasks, and so on. With regard to the basic part of our brain, the structure that's most notable for thermoregulation is the hypothalamus. In your ninja notes, I refer to the hypothalamus as a thermostat. Just like you would set the thermostat to a specific temperature in your apartment or house, when the temperature gets outside of that range, your HVAC systems will either heat or cool that living space to try and get you back to that set point. Within your body, That set point is about 37 degrees Celsius, which is about 98.6 degrees Fahrenheit. Now this temperature would be indicative of what we refer to as your core body temperature. And that core body temperature is essentially the blood temperature as measured by the hypothalamus. So something a little more centrally located. When that core temperature changes based on the type of environment an individual's in. For instance, if they're in a hot environment, if the core temperature gets too high, let's say about 39 to 40 degrees Celsius, the hypothalamus registers that as being too hot. You're hyperthermic, and it will then initiate a variety of involuntary responses to try and bring that core temperature back down to something thermoneutral. And I'll discuss that in a specific episode to come. If your core temperature was to drop too low, maybe it's 34 or 35 degrees, we would call that hypothermic. It's too cold, and yet again, your hypothalamus will initiate a variety of involuntary responses to try and bring that back up. So this 37 degrees under a variety of normal circumstances is most humans' set point, and the hypothalamus does a really good job of initiating involuntary responses to keep us really close to that. In fact, it does such a good job, our operational range is actually rather small. I mean, from here to there, that's about 4 degrees Celsius or maybe 8 to 10 degrees Fahrenheit. You're not going to change temperature that much in a variety of environments, even with exercise, because the hypothalamus will work quickly and powerfully to initiate those responses. The last thing that I want to mention here is that you've got temperature sensors in your skin. We call those cutaneous thermoreceptors. And those receptors can help you perceive what the temperature is outside before we see changes in core body temperature. So when you walk outside, if it's cold, you might immediately recognize it's cold. And the reason for that is that cold information is sent to the thinking part of your brain, the cerebral cortex, which then allows you to make some voluntary decisions on, oh, maybe I should wear some warmer clothes today. Together, these cutaneous thermoreceptors and that hypothalamus can work to help keep you right around that 37 degrees or Goldilocks number. So how is it then that the hypothalamus is able to make changes in core temperature? Well, there's 4 basic heat transfer mechanisms. This is a physics thing that our body can use to either conserve heat or dissipate heat. Before I discuss the 4 heat transfer mechanisms I've got illustrated here for you, I want to convey a very simple point with heat transfer. Whenever one object comes in contact with another object, the warmer object transfers heat to the less warm object, always. So you can't transfer cold. Cold really isn't a thing in physics. There's just heat or the absence of it. So when something's warmer, it has heat to give to something that has less heat. And you'll see how that gets exemplified in some of these different heat transfer mechanisms. The first one, in reference to your ninja notes, is radiation. Radiation is the direct transfer of heat from an object to something else. The best example that I can think of would be the sun radiating heat on our planet. You know what that's like, right? When you move from shade to the sun, you instantly feel that warmth. And of course, you understand that the days when the sun is out are warmer than the nights when the sun is away. So there is a radiation from the sun that directly transfers heat from that star to our planet. Please note then that when you're exercising, the sun or perhaps the ground will generally be radiating heat towards our body. That's a really common example of that. Another heat transfer mechanism that you'll see in your ninja notes is known as convection. So convection refers to a fluid such as air or water moving across a solid, and this fluid is either bringing heat to the solid to warm it up, or it's taking heat away to cool it down. As I've mentioned already, whatever's the warmer object will transfer heat to the cooler thing. So if you were in a cold whirlpool, for instance, for those of you who have experienced that before, your body is warmer than the water. So since that water is moving by your skin rather rapidly, it's going to take that heat away from your body rapidly, which cools you down fast, sometimes even too fast. You got to be careful with that. On the flip side, if you're in a hot tub, the water temperature is warmer than your body is. And since that water is moving around, it's going to bring heat to your body and it's going to warm you up rather rapidly. So convection, as we experience it in most circumstances, would usually be contact with water or air moving across our skin to warm us up or cool us down. The third heat transfer mechanism I want to speak to is conduction. It's just like convection, but instead of a fluid-solid interaction, we have a solid-solid interaction. So if I was to touch this wall right here, if I'm warmer than the wall, I transfer heat to the wall. If the wall's warmer than me, it transfers heat to me. And you felt this before. If you've ever put on some wet clothes and you immediately felt that chill, it's a great example of conduction. You were conducting heat to those cold clothes. Other side of that coin, if you've ever put on clothes that came straight out of the dryer, they're really warm, warmer than your body. And as soon as you put them on, you're like, oh, I mean, you immediately sense that heat, right? That's another example of conduction, solid-solid interaction. The fourth heat transfer mechanism I'd like to speak to, and the most important as it relates to human exercise and performance, is evaporation. So whenever water evaporates, the heat that was trapped in that water basically just poof, goes into thin air. And evaporation often works with convection to help dissipate heat away from our body in an exercise scenario. Now that water is coming from sweat. So our sweat response is one of the most powerful ways that we can help dissipate heat. In fact, I've heard mentioned that it accounts for up to 80% of our ability to cool ourselves. Here's a quick ninja point on that. Humans, as mammals, are rather unique in that we have sweat glands all over our skin. We can sweat all over, and that presents a tremendous amount of surface area to help dissipate heat during exercise. Most other critters don't have that. Good example is a dog. Dogs can't sweat. So the way that they would dissipate heat is they would stick that tongue out, and their tongues are really large, and that's a lot of surface area. That's how they're trying to essentially use evaporation and convection together to dissipate heat. An example of critters that can sweat like we do are horses. It's one example of why horses are such good endurance animals, because they can sweat while they're doing exercise and thermoregulate better than a lot of other animals. And to further drive this ninja point home, the fact that we can sweat and most critters can't is the whole reason why persistence hunting is even possible. So not a lot of groups in the world now rely or even use persistence hunting more. And what persistence hunting is you get a group of people together, and let's just say they're chasing after a gazelle. There's no way that any of those humans is going to outrun a gazelle. They're just too fast, right? However, humans can thermoregulate better than the gazelles. So you've got this pack of people come across a group of gazelles. The gazelles are immediately spooked and they just bolt. They start running and they outsprint the humans easily, right? But the humans don't have to sprint. They just have to keep jogging along at a reasonable pace, sweating all the way, evaporating, cooling. And while the gazelles are running, their core temperature is rising rapidly because they can't dissipate their heat very well. And eventually, they start to get too hot, so they stop to rest and bring that core temperature down. Well, while they're resting, that group of people is just trotting along, catching up. And so it goes for miles at a time, maybe 5-10 miles. That's why it's called persistence hunting. And every single time they come across the gazelle, gets spooked, boom, goes. But it can't run as far before it hits the red line. And that means that that group of people gets closer and closer and closer to the gazelle, to the point that the gazelle essentially suffers heat exhaustion or heat stroke and can't run away anymore. That's when the group of people can move on in to take that animal. The fact that we can sweat all over and use this evaporative heat transfer mechanism to dissipate our heat gives us an evolutionary advantage over a lot of other critters, and also helps explain why horses are just amazing long-distance critters in and of themselves. So in an exercise or performance situation, we're typically using all 4 of these heat transfer mechanisms to either conserve or dissipate heat. And very often, in reference to your ninja slides, you'll see that there are mechanisms working against one another. So the goal is to be smart, is to be strategic, such that you can use certain heat transfer mechanisms to your advantage to either conserve or dissipate heat as needed. And I'll speak about that a little bit more specifically as I get into each of the individual episodes for cold and heat physiology. And that's it. We're all done. I encourage you to start checking out some of the other environmental physiology episodes. The next one in the series would be cold physiology, and you get to see some of these mechanisms in more detail in more specific circumstances. Have a great day, ninjas.